Okay, I realized when I was kind of writing some more words about that last bit of vocabulary that I ran over the length of that video. So I'm sorry. I'm going to like truncate it because we won't actually use this for a little bit. So just as long as you've had this exposure to that definition of a differential operator, know that we'll use it later. And that's going to be enough for us. So the wrap up for this video is on that slide. Usually I go back to the beginning first. That's my bad. So here's what I told you we would cover. Background for higher order equations. We define the problem we're thinking about, have another initial value problem theorem, and then talk about fundamental solution sets. That would kind of be made up of a couple different ideas: superposition, linear independence, and maybe having to make extra considerations for non-homogeneous equations. So we defined what we mean by an nth order differential equation. We're thinking about these linear things with n derivatives in them and potentially a non-homogeneous part. And we noted that an initial value problem for this type of equation is going to have n initial conditions. We wrote down our initial value problem theorem. It's kind of similar to our initial value problem theorem for first order equations, just more conditions. And then we talked about how now that we have multiple initial conditions, we could think about specifying conditions at multiple points instead. And that's a valid way to write down something called a boundary value problem. But sort of existence and uniqueness for these things isn't the same as existence and uniqueness for initial value problems. And we did this example that kind of demonstrated the different ways that could turn out, either having too many solutions, only trivial solutions, or no solutions, where an initial value problem would always have exactly one solution. And then we finally got to talking about how we're going to write down solutions to this type of thing. We broke up our cases into homogeneous and non-homogeneous, and we gave this idea of superposition before we actually defined it as superposition. And we said that functions that we put together to form solutions to differential equations should have a couple different properties. They should be linearly independent, and you should have n of them. I guess kind of a secret condition was that they have to be solutions. That was written in the way it was given to you. And then we did an example where we were given two things. We checked that they were solutions. We checked that there were two and the equation was second order. And then we checked that they were linearly independent using this Wronskian idea. And then once we did that, we said, okay, when you meet these special conditions, you can write that they're a fundamental solution set, and you put together the general solution as a linear combination. We called that idea superposition. And we said that we could go ahead and do the same thing with particular solutions to address our non-homogeneous case. And then we talked about all the vocabulary that we had kind of put to the side up until then, that we were using superposition, that superposition has this special extension for finding particular solutions, and then that we can represent differential equations as operators, and it's a linear operator that has some neat properties that you didn't get to actually see. So on this slide, I wrote down all those things that we talked about. What are these nth order differential equations we're going to be solving? What conditions do we have to guarantee unique solutions to initial value problems? The boundary value problems are kind of different than that. And then we spent a lot of time talking about creating general solutions. And I wrote those important steps down here again. So you're going to find n things. You're going to check that those n things are solutions. You're going to verify that they're linearly independent using the Wronskian. And then you're going to use superposition to build general solutions. That just means multiply by constants and add everything together. So this was sort of similar to the first section of class, was a lot of words that hopefully became more comfortable as you learned what a differential equation actually was. This is a lot of foundation we need for higher order equations. Hopefully, as we work with these ideas of superposition and look at initial value problems, they'll become more manageable. But for now, your practice problem is just going to be to check that y1 equal to e to the x and y2 equal to e to the 2x form a fundamental solution set for this differential equation. So you're just going to repeat what I did for this example using your different exponential functions. So go ahead and work on that, and I will see you in class.